So we move into this first morning session of 4 exciting, very interesting talks, starting with, the session is generally called Insights. So what sort of insights can we generate when we bring the different kinds of competencies from both geodesign and CyberGIS principles. The first presentation, extending WorldMap and to make easier for humanities and others to find, use, and publish geospatial information. Wendy, you ready?
Thanks.
Do you want me to give you indications of time, or you're okay?
Give me indication of time.
Okay.
Yes.
How much? 5 minutes left?
5 minutes left would be good. Thank you. Wow, it makes me nervous to come up here right after Mike's exciting talk. My brain is submerged into geodesign. I have to pull it out and try to remember what I'm supposed to talk about here. I'm not sure about whether it's insight or not. What I prepared is to introduce to you a project we're working on and let you tell me whether that is a CyberGIS project, does it belong to the insight, or it's just a genuine effort to help the humanities. This work, as you can see, is done by a team led by Professor Peter Bo, who himself is a historian, vice provost at Harvard, and also my colleagues at the Center for Geographic Analysis, Ben Lewis, and a number of other people. So I'm really the tag-on. I just happen to be here, so I'm speaking mostly for them. And you have to excuse me if I can't answer all the questions you have about this. So the essence of this project is a National Endowment for the Humanities grant, is to make a web-based collaborative GIS platform we built called WorldMap better. Better in the sense to making data outside of our own platform more readily available, and also making our capabilities of the system directly usable from other platforms that the humanities and others would choose to use. So really, this is a big collaborative attempt. So what is WorldMap? For those of you who haven't heard about it, I think some of you have. In a nutshell, it is a web-based, as I said, web-based open source mapping platform for collaborative mapping. It's designed to lower barriers for researchers who are not GI scientists, not even geographers, because we don't have any at Harvard, to really use the geospatial technology. Again, it's service-oriented architecture, open source. It's on GitHub's, what we talked about a lot yesterday. And it's very basic. It helps the researchers of any discipline, health, design, history, sociology, environmental scientists, you name it, any field, that don't have the patience to learn even ArcGIS, can come up to the browser, organize their own data, maybe they get from elsewhere, maybe they generate themselves, visualize it, match it up, publish it online, share with their colleagues or share with the globe, and really form this collaborative investigation team and just go on with your own subject of interest. We started this in late 2010 and released a beta a year after, less than a year after actually. And since then, this is usage statistics. It's cumulative, so over 10,000 registered users and so on. I'm not going to read the slides, but you get an idea. It's been modestly well received, let me say that. There's no comparison to the big platforms like ArcGIS Online or Google Earth or Google Map. It's not at that level, but nonetheless well received by the academic field, those who don't really have strong GIS support in their own discipline. So it's built, the reason that we could build it by one programmer within less than a year and then keep growing with that very constrained resource is because we built on the open source platform. A lot of these components are developed by the broader open source community. I'm not a developer myself, so I wouldn't be able to explain a whole lot of the details that you see in the chart, but I'm sure a lot of you probably know more than I do on these different components. And the contributing organizations, GeoNode being the main component that we build on top, is supported by many organizations, and we took it, we enhanced it, and we receive a lot of support, small contributions to enhance it, particularly for the WorldMap implementation of GeoNode. So we're using a loosely coupled approach for system integration, or maybe interoperability rather than integration. As the panel yesterday afternoon had indicated, whatever works, right? All we want is to make the user accessible to different platforms through our system. And the data connects to many of these sources, media, public media, or other established platforms. And overall, our goal is, again, to lower the barrier to geodata access across disciplines so that our system, having its own data repository, also connecting to all the other, is this a laser pointer? Which way is, sorry, should have learned how to use it. Never mind, maybe I can use this. Yeah, so representing all the other systems out here, and then you can have institutional usage, individual usage, classroom usage, always focused on contributing data from their local sources and access data contributed by the other systems or other users. So with that, the NEH gave us this mandate to make it better. Make it better in these 5 different ways. Find the web map services, or REST services, right, from the GeoWeb. There are so many out there, but not so easily discoverable, right? So this goes back to yesterday's panel about discovery, harmonization, right? Analysis, validation, right? And publication. So really just serving that procedure, finding things, adding their own content, and also when they don't have IT support, if they have a data layer they want to offer to the world to use, right? They can come to this browser and be able to do that. So when you allow people to contribute in a crowdsourced environment, metadata is weak. People don't really go structured way to enter like library standard metadata. So how do you find the relevant information from that big pool of crowdsourced content? And then also time. How do you enable time in this system? So these are the core issues that we are set off to address in this grant. Building the comprehensive registry of map services. Yesterday, there was another presentation about web services for geoprocessing. Ours is the registry of map services, meaning find data, right? And be able to search them intelligently and mesh up with researchers' contributed content. So in order to search effectively, we taken a few different approaches. One is to enable time, so that you limit it by time, by space, by feature level content, and also by metadata keyword, of course. That's a given. And then we want to build the wisdom of crowd into the search mechanism, meaning layers being used often will have a higher rank. Layers that users rank high will come up in the search at a higher rank. And also institutional users could even certify their layers, saying these are vetted by our organization, therefore they're more trustworthy and they can be searched. When they're being searched, they come up higher. And then in the attempt to create this global service registry, this is map service data, right? We found through some really painstaking effort that trying to find whether there's already built methodology or system that could give us a comprehensive entry point to the GIS data services out there, and we did not find that, right? So millions of map layers all served out, exposed on the web. There's no easy way to find what you need from that. So we are attempt to build a registry for that and turn around and serve it out as an API. So any system can search that and then bring that service to their system. And we can do the same, of course, to our native system. And usage statistics to improve the search. This is just a very quick example of how we justify our estimate of millions of map services out there. That's not very easy to discover. We did a search by the default string text for Esri's REST services. Yesterday, Don was saying that there are millions of data layers just in ArcGIS Online alone, and it's growing so fast. But for people who don't have an ArcGIS Online organizational account, how can they use that? This, I hope, will provide a channel for them to do that. And then, of course, the web map services, WMS, there are also many, many thousands of them. And this is by no means complete, right? But it's our first attempt to start building that. And in doing that, we think the major challenges, metadata weak, as I said, some of the map services, hundreds of layers, but not a whole lot of metadata. And we're trying to use usage statistics, excuse me, and user tagging to improve that gradually. Projection, as soon as you try to mash up different data sources together in a mapping environment, projection becomes a challenge, and we go through the cascading projection procedure to bring them together. Persistency, when you don't know who serves out the data, they're just out there. Sometimes they go down, sometimes they're not, responding. We try to mitigate that by caching, and we're also building a uptime statistics to help user determine whether this source is reliable or not. We're building the central index using statistics and performance, also through caching that we're trying to improve the performance. So once we gather all that information, we turn it around and make it an open API so that people can draw from this. And I'm not going to read all this words, and this is a mock-up of the service search that we will offer to other systems, and users come to our system so that you can slice and dice it by your interest, geographic bounding box, time, the type, the category, right, and the keyword, so that and the keyword could penetrate down into feature level rather than just depending on metadata. So this is a very rough sketch of explaining what we mean. You have so many sources, coming in through the crowd, through the cloud, right? The ArcGIS Online, the REST services, the WMS. It comes in, right? We crawl it and build an index. We build the uptime checker to check on the reliability of it. We receive users' contribution to add to what we didn't crawl, didn't find, and gradually build that up too. And then we do the cascading reprojection, right? Caching to make it more persistent and reliable, right? We have our local services of user contributing layers to our system, and we turn around, serve them out as a WMS, and the core functions right here. Through the service registry and API, we give it out back to the users. So anyone using any mapping system who can consume a WMS would be able to get the contents that we aggregate through our registry. And again, the time-enabled part is a relatively independent effort. Part of this grant is because of the humanities focus, right? So much historical content. We have place name databases, but they're scattered. They don't talk to one another. Hard to use them together. Users have data. They have timestamps on their data. They may not call it a gazetteer, but it can be used as a gazetteer as long as it has a place name in it. So we allow users to contribute their layers and designate a column calling this is the place name, and here's our timestamp. Then it becomes a customized small temporal gazetteer, and they contribute to a crowdsourced pool of it, a general gazetteer as well. So our interface will be able to allow users to search just their own, a few famous ones, geonames, maybe Google place name or something else, or all of it. When they search all of it, it's not, it doesn't eliminate duplication. So attestation and disambiguity, those are left to be resolved in another effort. But we're starting to at least allow users to contribute and to start using their own. So by doing that, our focus is to serve the humanities through this grant, right? Giving them a low-cost entry into doing spatial digital humanity, which, by the way, is flourishing in the humanities field, and eliminating duplication effort in the routine spatial tasks, right? Making their research material. Yesterday we talked about you publish a paper and you throw away your data, such a huge waste. Now they have a permanent place to put their data up there and share it and let others validate that, enhance that. So this is, and also using the spatial visualization on that. So a big summary keyword is collaboration. So when we have this, right, then I saw Xiaowen's invitation to this event, and I said, I wonder what we are doing here has anything to do with CyberGIS. We started it without a lot of thinking about the CyberGIS concept. But then when I saw Xiaowen's message and think, maybe it is. So I went and did my crash course on CyberGIS, looking at what's the definition, and the concept I realized had been evolving. I'm not going to read all this, but you get the idea, right? When I read through different presentations and papers, I see how the CyberGIS concept had changed, and there are different angles in looking at it, right? So through all these, sorry I missed yesterday mornings, or I would have one more slide to continue this learning. But in general, I quickly summarized a few keywords that my mind can grasp, may not be complete, but one is cyber infrastructure based, and our effort is, right? It's hosted on Amazon, it's service-oriented, it's web-based UI. The other is high-performing. I'm not sure about high-performing in terms of lightning fast, but considering the volume of data we're serving and the number of users are using it, we are improving the performance of traditional GIS or web-based GIS. It's our effort. The caching, the faceted search is approaching, improving performance. Whether it's high enough is out there to be judged, right? Distributed, certainly, and collaboration is, again, the keyword that we're really focusing on. So I think our effort is relevant to CyberGIS, and I would like to hear feedbacks from the audience here on that. And really, to summarize, our objective is to make the system an open and accessible CyberGIS, if I could use that term. Open registration, open access to data, open service protocols, open data formats, open source code, of course, and usable on any operating system, so being platform independent. And with that, I don't know whether we want to get into a lot of these future perspectives and challenges. I can always get into it if you have questions on that. I just want to show the real people, the key people behind this project, not me, but Professor Peter Bo, who is the director of our Center for Geographic Analysis, and Professor Suzanne Blier, a African arts and architecture scholar who spearheaded the previous system that lead into WorldMap, which we called African Map to begin with in 2008, continue to be a champion, a power user of our system. Ben Lewis is the architect of the system, and Matt Bertrand is the single-handed programmer who built the thing. So with that, I hope, well, there are more links that if you want more information, but I'd like to try to answer questions if there's any.
Well, in the interest of time, maybe we can take one question, Don, and then would the next speaker come up and get set? Yes.
Thank you. So Wendy, I think your presentation is absolutely perfectly placed after Mike's. Really enjoyed it, especially with the emphasis on the humanities. Yeah. And I think it is very much CyberGIS. My question is, Mike said that geodesign in the context of the academy is an opportunity for the humanities and the sciences to talk, and CyberGIS is the bridge. And I think you are providing that bridge. So my question is, I know that you are getting people in the humanities to collaborate. Are you seeing any infusion of social scientists or scientists using WorldMap and entering into that collaboration?
Yes, I wish I had the user statistic breakdown further. We do have that data, and the humanities are using it, big time. Social scientists, yes, a lot of usage. From the science field, it's a bit skewed. The geologists, the environmental scientists, they use it. Forestry, they use it. Evolutionary biology. Even we're starting to collaborate with astronomers. But I had a hard time to get the hardcore computer scientists and digital visualization scholars to join force with us. So that's our challenge. Also an unexpected, well, maybe I should, is business. Our business school professors using it. Well, the usual suspects, public health and planning, those are definitely in. So the user base, this covers a lot of disciplines. Yes.
Thank you so much for your presentation. This is very interesting work. The next speaker, thank you, Wendy. Next speaker is Tapani Sarjakoski, and it looks like we're moving into big data and big compute, and he's going to be talking to us on needs and solution directions for high-performance geocomputing.
So, thank you. It's a true pleasure to be here. I'm really happy that I got the invitation to come over here. So, actually, that was not. That was just starting slide.
That's better.
Yeah. I come from the Finnish Geodetic Institute. We are a research institute, very small one, 100 persons, a governmental one, and actually starting the 1st of January next year, we will be merged to be a part of National Land Survey. National Land Survey is a bit similar to USGS. So I guess starting then we will be called, our unit will be called Finnish Geospatial Research Institute. I'm going to speak about our perspective, how to build up high-performance GIS solutions. There are going to be actually 2 cases which I'm going to use as a demonstration what we are doing. My talk is, and our research is made jointly with Åbo Academy University Department of Information Technology with Jan Westerholm. He's a professor there. Juha Oksanen is a team leader in my department. And regarding my department, just a quick introduction. We have 3 research teams, one on analysis and visualization, one on interoperability and web services, and one on user interfaces and integrated our GIS solutions. That sort of demonstrates that we are not, so to say, thematically oriented, but we are rather doing generic GIS, computer-oriented GIS research. My presentation is based very much on 2 research grants. One is called Quick Response Uncertainty-Aware Geocomputation for Very Large Datasets. That's by the Academy of Finland, our National Science Foundation. And second is, has a kind of fancy name, Revolution of Location-Based Services, Embedded Data Refinement in Service Processes from Massive Geospatial Datasets. That's from the Finnish Funding Agency for Technology and Innovation, which is more industry-oriented research, we have industry partners there. And there's also a link to a research infrastructure initiative called OGIR, Open Geospatial Information Infrastructure for Research. And in that one, the goals are very much parallel with those in CyberGIS, actually. It's not running yet, but it's on the so-called roadmap of the Academy of Finland. I can say something later on. Okay, I try to make often the titles of the research proposals to be kind of short abstracts. And in this case, the first one tells something quick response. We want to get something very quickly. Uncertainty aware. We want the uncertainty aspect to be in the analysis and also the very large data sets. That's in the first project. And in the second one, the keyword is perhaps the embedded. We see it that way that high performance computing is also used such that if you look at it from the end user's point of view, he doesn't really know that there's some kind of high performance computing going on. It's totally hidden from the user. Needs about for high performance geocomputing. Well, I think these have been said many times during this conference already. Increased data size, repeated computations, heavy modeling, multi-color simulation, on-demand computation and animation, so on. Our special interest is in uncertainty-aware geospatial analysis. And the reason for that is that, as we know, the data is never perfect, practically speaking, and the models are not perfect. But if you look at the practice, well, the theories are rather well established in many aspects. If you look at the practices, this kind of stochastic error propagation and sensitivity analysis is not really done too much in real life yet. So it rather has been a research topic. I use this as one example where we sort of see it. When Google Maps came years ago, in the first versions, you only got one line, one route from point A to point B. But in the current versions, you currently actually, as a default, you get at least 2 or 3 options. So that's a kind of very simple way to get to a user some kind of understanding of the sensitivity. So perhaps the optimal route is not the optimal route for me. So I think this is kind of indication. Yes, there is a true real-life need for uncertainty and sensitivity analysis. Okay, then now I go to the cases. The first case is related to the drainage basis analysis and to the digital elevation models. We heard yesterday already 2 similar talks. In Finland, the Finnish Environmental Institute maintains the national drainage basin systems about lakes, rivers, and other water flows. Those are topologically connected and so on. And we want to use digital elevation models to find out the boundaries of the drainage basins on several levels of hierarchies. So we take the elevation models. The current ones which we have basically the best ones have 10-meter resolutions. And then for the neighboring countries, we use the GEDIM data just to get some neighbor country coverage as well. And the main sort of intermediate product is flow direction grid. And well, I just mention also this, that LiDAR data is coming available, and once that is available, the amount of data will be much more. The coverage will be complete in 2020. Okay, as I said, flow direction grid is the main intermediate product. And now if you look at the situation from the user's point of view, one of the important tools is their so-called an interactive tool where the user can point out an outlet point, and then in an interactive process he gets the boundaries for that catchment area. And our question is how to get the uncertainty information for the user. We have made some usability analysis based on static maps that the users really like to have that kind of information. Perhaps this is a better picture because it shows that there are, when you make uncertainty analysis for the drainage basins, there are really different cases. In some cases, the boundary is very well defined. In some other cases, it's very spread, and in other cases, there are many alternatives. And the way to do it is multicolor simulation. You just repeat the analysis many times and have some kind of error model for the digital elevation model. I don't go to the details. I think you know that very well. But our interest has now been how to make it quick. One piece of our work is full graphics processing unit implementation of the uncertainty-aware drainage basin lineation. There are two aspects in that one that our interest has been, that how to make it truly graphic processing unit based, because that way you can avoid data traffic. And the other aspect has been the speed up. In this case, if you take the total, we were able to get 10 times speed up. That's actually part of the story, because if you would compare our program to ArcGIS solutions, which we have used, actually there the speed up ratio is 100 times. Why is it so? Our software is especially made for this task. It doesn't have that kind of overhead things which you have in a general purpose software. But it really shows that you can do something if you take a current software and so on. So that 10 times was in this case, but of course it's, or 11 cases, of course it's a moving target. Then our next step is to run that on the high performance computer. That case was running on a single desktop with a one GPU. We are using the Finnish CSC facilities. That's our computing center, located about 300 kilometers from the Arctic Circle. Actually, the cooling situation is rather nice there. You have a lot of cool waters around. They have a new Bull installation with the 38 nodes. Each of them has 2 GPUs. And we have made implementation already there. Now, the key issue in this kind of environment is, as you know, how to make a spatial partitioning. We are using raster data, and the spatial partitioning is basically simple. We just divide it into blocks. And so to say, each node owns one of the blocks, and then those nodes have to communicate with each other. If you look at the steps here, for many of the phases, it's really straightforward. There is no interaction between the blocks. When you generate random fields, that's simply block by block. But you have to synchronize the borders. And some phases are sort of more tedious, like a field decompression. Basically, you work all the blocks parallel, but then once you have finished with the block, you have to propagate the consequences to the other blocks, and there might be several iterations. So that's the results of that one will be later this year. The second case is related to flood analysis. Currently, we have static flood maps in Finland, but how about if we would have an interactive system where the uncertainty analysis would be involved? And we are making a demonstration for that one currently. Basically, if one more time, currently the flood analysis is such that you have static maps. The dark blue is the water area, and the light blue is the area for forecasted flood. And what we want to have some kind of uncertainty information also about flooding. What is interesting here that the Finnish Meteorological Institute provides a forecast of the expected sea level. It's available through our access interface. It's made every 6 hours. It's a short-term forecast. I think it covers 2 days or so. And now the idea is that the user should have an interactive tool to make more detailed look analysis or investigation where the flooding might be in near future. So you have there, let me see. So one diagram of the systems, as I said, that we use web feature service provided by the Finnish Meteorological Institute, get the forecast, and then very typical web map implementations to provide the interface for the map. So basically, you have there the time slider where you can study this area. The more detailed results will be available later this year also for this study. Then something from the more general aspect here. You might know that in Europe we have so-called INSPIRE directive, which is supposed to guide how the national spatial data infrastructures are established. And the implementation is going on currently in the countries. You might criticize that process in many ways. It's rather bureaucratic and so on, but it has at least resulted in the awareness of that web services are a tool for building up these kind of things. Anyhow, in the spatial data infrastructure as seen in INSPIRE and also in our country, the basic idea is that at the bottom you have the data service, and of course you have the metadata services and the processing services in the middle, and finally at the user applications. And when I relate that to the high performance computing, in a research proposal to the Academy of Finland, we used this diagram to illustrate the situations that basically you have the national spatial data infrastructure where you have all the data, and somewhere you have a processing service for high performance geospatial analysis. That was sort of our initial mindset. But it has become more apparent for us that actually that doesn't really work well, but you rather have to have a high performance environment where you have the processing capabilities and also the large data sets situated next to the processing capabilities. That was also mentioned by Lynn yesterday, and it seems to be the only practical way to do it today. Then I just mentioned this. In this another project, we also make some other things than this flooding analysis. We take the our cooperator is there, the sports tracker company, and some of you might know that sports tracker company has services and mobile apps where you can upload your workouts into the cloud, and we analyze that data to get interesting results, and the heat maps are the way to do it. Well, what is interesting in this one is the thing that it's fully real time. We don't make static maps, but rather everything is made in real time, and you might go later on to the web page of these applications and have a look of that one. So very quick intro. So that was the end. Thanks.
Thank you. Very interesting presentation. Questions from the audience? Mary in the back.
A clarifying question. The little O-G-I-I-R. For that, is there information available about that online somewhere?
Do you mind repeating the question? So
Yeah, is there information about this project initiative? It was. I'm not sure. The Academy of Finland has published the so-called roadmap for the Finnish research infrastructures, and if they have the English version in the web, it's there, but I'm not sure. So it's really brief because it's the project is in a development phase yet. So
I had a question if there was nobody else. There was a map that you had on the watersheds. Yeah, it's in pink. Next one, probably. Yes. No,
pink?
that one. Yeah.
This one.
Yeah. I was trying to understand what the legends actually meant.
Well, that's finished. It's a probability.
Okay.
The dark pink is in the dark pink area. the boundary or the watershed is most likely on the dark pink area, and on the lighter the color is, the less probably.
Okay, so it's a range of
Yeah,
high,
exactly,
medium,
yeah,
low
yeah.
type probabilities. Okay, great. That's
Actually, this sort of illustrates it's in a more clear way. So basically, you have the probability there.
okay, great. Thank you. Any other question for Tapani? Mike?
I understand that you randomize the DEM,
Yeah,
but do you also randomize the flow direction?
the
Flow direction? Are you using a straightforward D8 or do you?
yeah, we don't randomize.
Because that in itself is a source of uncertainty, isn't it?
Yeah, I was thinking about that yesterday because we had a related presentation, but actually, because you randomize the elevation model, basically, in an indirect way, also the flow directions become randomized. So we use autocorrelation functions and so on. Yeah.
Satish, one more question.
So I think you mentioned about the file I/O problem and how the file, the storage and the data, how that should be available with the high performance computing centers or nearby.
Sorry, could
In
you?
terms of file I/O, in terms of getting the data into the GPUs and the
Okay.
computation,
Yeah.
how much of that is a problem right now?
I didn't say anything about that, and it's not an issue because in this case, not really, because if you assume that the data is next to the computer, so we only have to read the data once and write once because the nodes own the data throughout the process. Of course, if you don't have nodes enough that you will start to swap, then it's a different case, but we want to avoid the swapping. So basically, it's an issue, not an issue. But
Just following on that, I understand the representation of communications here, but then your computational intensity, and just in this one, it also a function of your stream network density, right? So the more streams you have going from one partition to the other, the communications goes.
yeah, it's actually my colleague just pointed out that this, from the computation point of view, this kind of rigid partitioning is not always optimal because it doesn't balance the computation. Some of the nodes might be waiting a lot because the others have exceeded.
All right, so thank you so much for an excellent presentation. Lee Ann's presentation is next on space-time analysis of big data, multi-level modeling approach.
Can you guys hear me? All right. First, I would like to thank Wen and CyberGIS'14 organizing committee. Thank you for giving me this chance to come here and present my work. This work is part of our CDI project outcome, which I presented a similar talk a few days ago during our 2014 CyberGIS Specialist Meeting. Well, my previous title was Space-Time Analysis of Big Data, a Multi-Level Modeling Approach. But even though big data is a buzzword and it's very popular, but I think my work is not so much about big data, so I would like to change the title. Right now, it's all about time. This time could be chronological time or chronological time, as May just mentioned yesterday. And also, as Mike just mentioned, geo-design, we are concerned about time. So my talk today is about latent trajectory models for space-time analysis. First, I want to thank NSF, the Cyber-Enabled Discovery and Innovation Program, as well as the Dynamics for Coupled Natural and Human Systems program. And at the same time, I want to thank the students who work with me, in these years. Well, first, a little bit of theoretical background, complex systems. I believe yesterday, one of you guys mentioned this. And I also like the complex system framework. Well, there are some confusions about complex systems. First, complex is not equal to complicated. Often we think, a complex system is a complicated system. Actually, no. Complex is opposite to interrelationship. It's too independent, okay? When we say something is complex, we say they are more or less, interconnected or interdependent. Complicated is opposite to simple. So very often, a complex system could be very complex, or could be very complicated. Second is chaotic. Complex systems, very often, they are chaotic, but they are not necessarily random. Even though oftentimes there's a huge amount of randomness, but chaotic is not equal to random. This is often something I have read recently, and also I heard from a recent, CDI meeting that we just had a few days ago. Well, in terms of complex system, I want to highlight two major features. The first one is disorganized complexity. So in this situation, the system has a huge amount of, parts or components, okay? And the instructions of these parts, we cannot, use, mathematics or any analytic, equations to quantify or to, categorize such, interactions. So usually we use probability, models. We use statistical models to, quantify this kind of complexity. The other kind of complexity is organized complexity. So usually it arises from non-random or correlated interactions between these parts. For example, we use simulation models like agent-based models to work on this type of complexity. Right now, one of my NS projects, we are building a parallel agent-based model, right, to deal with this type of interactions, simulations over time. And right now, it's a parallel, agent-based model. But I believe hopefully someone will help in the future when we have cyber ABM. That, well, that's just my, vision for the moment. But today, I'm going to talk about the first type of, complexity is disorganized, complexity. So usually as geographers and many space data analysis, we have data like this, okay? Over time, we have information landscape. Maybe this is not working. At time one, so 1, 2, 3, 4, and n represent some spatial units. Could be individual people, could be some parcels, could be some pixels, or any units that we are interested in. And at time 2, it involves time 3, the one in the middle, time 4, and time 5. The color represents the change of some characteristic. For example, could be the population density at, for example, if a circle is a county, okay? Could be some income level change. If the circles are individual like animals, could be, say, they are some behavior patterns, okay? In my Golden Monkey project, so all the circles or units could be monkeys, and we are trying to track their, where they go, how they, make use of the habitat and so on and so forth. As geographers, 1, 2, 3, 4, these units could be any pixels, for example, land parcels, pixels. Well, traditionally, when we have this kind of data, okay, we are strong in categorize spatial autocorrelation. So at one time point, we can say if the phenomena is spatially out-coordinated, okay, we have Morin's I, Gary's G, and so many indicators and methods to characterize the spatial variability. Or in social science, we are good at characterizing the time series or the temporal, heterogeneity. Or recently in space-time analysis, there is some space-time, distance or space-time heterogeneity, categorization. But there are some caveats for this traditional spatial analysis methods. I would argue, first is the temporal trend has not been fully or has not been enough, has not adequately, captured. The second is it's relatively weak in explaining the temporal trend. Why, for example? In one area, in one unit, there is an increasing trend. Why in another unit or another area, there's a decreasing trend? Or why in some places there is a periodic pattern? Okay, it rises and falls, like a sine or cosine pattern. So in traditional spatial analysis method, we don't have a strong, method for doing that. So right now, what I'm presenting for today is, why don't we think about the trajectory. For pixel 1, let's say, over time it increases, and then from time 1, time 2, time 3. Then from time 4 to time 5, it decreases a little bit. So if we think there is a linear pattern, then we use a linear line to characterize this, the data at these 5 points. For pixel 2 or spatial unit 2, well, it starts at a relatively low, starting point. Okay, if we use a linear trend, the intercept is lower, but the slope is also lower compared with point 1. Well, if we consider, point 3, then it's different in terms of the trajectory. Okay, well, then we go to point 4. Then it starts at a higher, intercept. And if we believe there is a, linear trend, it looks like this, okay? And the slope is lower than the number 1 and number 2, but it's probably higher than probably the same as number 2. Well, so my question, or what I'm proposing is, why don't we focus on these trajectories rather than focus on individual space-time measurements? Because usually our methods for today focuses on individual measurements at a specific time and a specific location. Okay, so the latent trajectory model is not new. Actually, in social science, demography, sociology, it has been well developed. But in GI science, arena, well, I haven't seen much, literature in this regard. But from my presentation later, you can see this might be potentially a good method for us to categorize the temporal trend. The underlying assumption is repeated measures over time for each unit, okay? There is some underlying or latent trajectory that give rise to these trajectories. For example, if I go back to this one, there might be some latent trajectory. So all these lines, okay, no matter it's the blue one, the light green one, or the brown one, there is some perturbation over that latent trajectory because of different geographic environment, socioeconomic reasons. These curves just move up or move down, or the slope maybe sometimes get a little bit, flat, sometimes a little bit more, bigger. So if this is a reasonable assumption, then actually in theory or in latent trajectory modeling, we can assume different type of latent trajectories. Okay, depending on the question, we may assume a linear trajectory or exponential trajectory or quadratic trajectory. There are many other trajectories that we can assume, either parametric or non-parametric. Okay, so in this situation, what the idea is, we don't regress or analyze each individual data point. Rather, we analyze the trajectories or the parameters of the trajectories. If it's a linear, say, trajectory, then the intercept and the slope is what we're interested in. We are concerned about what predictive variables may help us understand why for a certain place the intercept is this much rather than a big intercept. We are also using the same predictive variables to explain or to predict why for a certain spatial unit the slope is that big rather than this big. And we can explain why the slope or the intercept may change from the latent trajectory or the one that gives rise to all, but with different variations due to local data. So this is the idea. So later I'm going to present a case study. So here, this is the information landscape. We searched on CyberGIS server. We searched the keyword climate change on a weekly basis since 2011. So here I only picked up 5 to present to you guys. Okay, T1, T2, T3, T4, T5. Okay, so for you, I think the idea is if I give you this time series of spatial data, I call it spatial panel data. How are we going to analyze the temporal pattern as well as the spatial pattern that are hidden in these maps? Okay, so at this moment, I assume you trust our method for this information information collection. Okay, so for example, at time 1, we say some for the red, it means there is a high interest or high concern or high awareness of climate change in some places. So on the western coast, we see some hot spots. On the eastern coast, we see some cold spots as well as some hot spots. If time goes to T2, actually it's 3 months later, well, we see this kind of hot spots and cold spots shifted, to some degree. Well, if we use some traditional spatial autocorrelation or spatial analysis method, we can characterize at each time what's the Moran size. Are they spatially autocorrelated? I believe yes. If I calculate the Moran size, it should be a very positive and large number. But if I put all this data together, okay, if I present you the maps for 1,000 times, I don't think it's very helpful to say we calculate the spatial Moran size for 1,000 times from 2011 to 2014. Well, but here, this is what I got from these 5 maps as an example. So first, compared to global Moran size, if we can reasonably assume there's a linear trend, then that dashed line is the temporal characteristic of all the information landscapes I just presented to you. If you want to know the numbers for this linear line, the number is here. Basically, the intercept 3.0572 is intercept, which means the popularity for climate change on average at the time of beginning. Okay, thank you. It's 3.05. Well, more important is the T, 0.2592. This is kind of similar to the spatial Moran size for spatial analysis. So here's for temporal analysis. So here we see a strong, significant increase over time, which means the interest in climate change or the popularity of the idea of climate change increases over time. Well, however, you may or may not agree with me. There is a linear trend over time. So I also tried a quadratic, trajectory to characterize the dynamics of climate change over time. So in this situation, we can say it increases, from time 1, time 2, up to almost time 4. Then it decreases. Then, if we want to know if this is true, then for the third column, we know, okay, also there is a positive significant, intercept, which means it starts as a positive level. Then the T or the slope for the time is positive, which means it increases over time. But the T square is a negative number, which means over time, there is a deceleration, makes the increase, slower and slower, and finally goes down. Oops. Okay. So here I randomly pick up 5 counties of US. Well, I think one thing I want to say, so our data analysis unit is counties, all 300, almost 3,100 counties in US, okay? We collected, the popularity index for the climate change. So here I randomly pick up 5 counties. So you can say some of the counties we got increase, decrease, almost close to 0. All right, so in addition to make a link between cyberspace and real space data, we collect some data based on the US Census, based on American Community Survey, and so on and so forth. So we try to use percentage of Republicans, population density, urban population as percentage of urban population. The number of holidays in the summer, the drought days, the number of drought days, okay, with, okay. And also age with, the percentage of people who are older or older than 18 years old. We try to say, if we use this kind of data, can we predict, our population index? So right now, the idea is what predictive variables may help us to predict the temporal trend. As I said, the intercept or the slope, and so on. So in this case, I just want to show you one example. For percentage of Republicans, we can say the purple idea, the purple number. That one, if we assume a linear model, we can say the counties with lower values for percentage of Republicans, okay, it starts at the beginning of time, the counties with a higher percentage of Republicans have a lower value of popularity. But as time moves on, we have there is a positive slope, which means as time goes on, the popularity index goes up. But on the other hand, if we look at a quadratic model, we can say the intercept is non-significant. It's minus 18.96 or something like that. But in this case, the percentage of Republican increases over time, but the increase has a decelerating, factor, which means the more time we go, then the slower the increase in speed. This might be related with some of the Gallup survey results. So from September to October in 1997, we can see there's a strong gap between the Democrats and Republicans in believing there's a really anthropogenic or human-induced climate change. And also, if you look at the Gallup result in this slide, we can say as time goes on from 2001 to 2010, there is an increasing gap between the Republicans and the Democrats in believing there's a human-induced climate change. So our results, agree with what they have done in the Gallup, Gallup survey. So basically, in this research, first I want to discuss is the cyber popularity. Right now, we developed this index. We are using Twitter data, we are using Gallup data to verify what the popularity index means. So this is the first thing. Some cyberspace-derived indexes or data, we need some strong validation. So far, we are still doing that. But based on regression results, because of the agreement between the cyberspace regression data and the real, the Gallup survey data, we have a strong belief that this cyber-derived popularity index does mean something. Is that awareness of climate change, or the impact of strong climate change, or the interest in climate change? That's something we are discussing in the paper. The second point I want to bring is the trajectories share more important insights and are of our major interest in understanding the complex systems. So in this time, in this situation, we are not modeling any specific measurement at a time and a certain point. We are interested in the trajectory. This may be a good way to categorize the temporal trend in many GI science space-time data. The second one, in the future, this method may have applications in some vegetation index, for example. If you have remote sensing imageries and NDVI over a time series. So how would you categorize such NDVI change? That's one application. Also, when we have some regional space-time inequality analysis, like the work that Serge and his team has been doing. Also, we may use this application to analyze some Twitter data. So right now, we have collected a huge amount of Twitter data on flu, on political campaign, and some other topics. And also, I would say there is a potential application for the big data analysis. All right, thank you.
We'll take a couple of questions.
What happens, in your conceptual slide, you have those units, keep their unit identity all the time. What happens if you have units that split, merge with other units?
Well,
How would you handle those situations?
well, that's a good question. So if some units, okay.
Do you want to repeat that
Okay.
question?
Basically, his question is about, well,
No, you're already mic'd.
okay, in my representation, the units are consistent over time. What if some units merge or sometimes split? Then how are you going to deal with that? Is that your question? So basically, this question is not perfect. We assume some identical identities over time. But as I mentioned in one of my papers, we all say then process, they merge or they split. In that situation, as long as the major characteristic is not changing, we can still assume a consistent unit. For example, even if a certain area gets increased in size a little bit, but as long as the major thing you are looking at has not changed, then you can still assume the unit is consistent. There's no big change. Right? Okay.
In the trajectory slide that you had,
Uh-huh.
you have elements, and then you go to a trajectory slide, and you're moving from individual elements to a lumped characterization of the trend.
Of trend, yeah.
Kind of compromise there and say, what about pairwise elements, or 3 elements, or 4 elements? So,
For one trend, right?
well, what you're doing is decomposing the trend, because the overall trend that and there's only 5 that you have. 2 will make a trend, it's a line. 3 will make a trend, and so on. But you do the same thing with different granularities of the trend. So you could actually make the same argument you're making, but look at this in terms of just additional increments of what is the trend between 2. Over time, you've got 5 different levels, you've got 5 different time frames.
Yes.
And you have each of the elements. So what is the pairwise change from each of those 5
Okay.
time frames?
Okay, basically, the team is asking, right now I get one trend for all 5 or more measurements. What is the pairwise from time 1, time 2, time 2, time 3, or time 3 to time 5? Is that your question?
Yeah, will the same analytic process work?
Well, in this situation, we try to categorize the temporal trend using one type of latent trajectory, no matter it's linear or quadratic, or it's piecewise, or it's exponential. In your situation, if you want to do pairwise analysis, this method does not apply. I think the beauty or the strength of this method is we reduce the dimension of the data. If you have big data, you have 1,000 times. And if we do pairwise analysis, then the data amount is huge. And analysis, the time for computation is huge. But right now, if we have 1,000 measurements over time, we only need one trend, no matter it's a linear with curve. I think that's the strength, and also, to some degree, it's the weakness of this method.
We're in a CyberGIS meeting, so the comment about it's huge should really be the research challenge. essentially. So I'm just speculating that you could actually use the same method that you're proposing here, but look at different levels of granularity. So the multiple level things still apply.
Yeah, that's a good point. Maybe in the future we can take care of that issue.
I have a quick question.
Okay,
if you
sure,
don't mind.
please.
So, is it okay to assume that these kind of approaches would work for any classes of geographic data, or certain classes of geographic data? Because some of the variables you are trying to correlate.
Well,
are, you know, there is a lack of predictability, right? So it's physical data sets versus, you know, more dynamic data sets, for example, sentiments. It almost assumes, like the data set that you showed, that Republicans are always and forever will be opposed to a cause or a particular thing, right? And I don't know how strong that assumption could be. So when you go to trajectories in those cases where you know, our power of predictability is not very certain, does the power of these kind of techniques go down as opposed to like NDVI, which, you know, fairly certainly the response is more predictable?
Well, I would say this method can work as long as you organize that as the spatial panel data. And I think this is related to Shigong's question. If we can reasonably say the spatial unit is not changing over time, or the big characteristics of the spatial units are consistent over time, then we can use this method. So for example, we can use that to analyze data about individual, you know, persons, no matter they move over on the space over time, that's fine. We can use that to analyze NDVI of pixels over time. We can use that to analyze like sentiment. Also, we have in our CDI project, we have a sentiment analysis about climate change. We classify them into strongly, you know, positive about climate change, positive, neutral, negative, and strongly negative. We are going to use this method to say why the sentiment about climate change is changing over time and over space. This is actually the thing we are doing now.
Thank you.
Okay, thank you.
All right, so keeping up with the tradition of this conference, we are running slightly behind, but we will get to the end. Our last speaker is Sushil Prasad, and I'll let him take over.
Thank you for the invitation. I think I was out of line, not submitting into proper place. So I'm a computer scientist, and this is a collaboration with Shekhar, who is also a computer scientist. And we are very interested in this area, and in our past few years, what we have been doing. Of course, I'm new in this community. So the main purpose, of course, is to relate what we have been doing, highlight some of the activities, and maybe find some collaboration. So that's the main thing. Satish Shekhar, of course, you all know, does great work in data mining, especially in the transportation and special geoscience. And we have a bunch of students, more have joined in, and so they are looking for work. So please suggest. One thing that I actually wanted to point out, there was a question yesterday about why parallel processing, why CyberGIS, what is so much good about speed. I think it's not just about real-time decision making, performance monitoring, and then so forth. That's of course one of the components that enables you can only do certain things if you have that kind of speed. But it's also actually about the speed itself. It's almost like the steamship versus the plane and the railway. So the entire thing actually changes. The landscape changes. Big capabilities come in. So really, this is very promising area, and the community actually is in the right path. So what I would like to actually argue today is definitely we need to do a lot of parallel processing. My area is parallel processing, by the way. But also we should actually look at shared memory parallel processing. And in fact, the talk from Finnish Institute, where they have used GPUs, in fact, that's the kind of thing that actually I like to see more of. So clearly we have shift in the architecture, computer architecture. So even your laptops actually are multi-core now, right? And actually they do have GPUs. The big computers, the clouds, the clusters, in fact, they also have GPUs. So the point is that definitely that's the way to go. And this also means there are new challenges, research challenges, both for the community, this community, and for computer scientists. And so coming from computer science point of view, actually I see a lot of interesting algorithmic work that can be done here. Okay. Also, more of the logistics part, with a single GPU, which has like 500 to 2,000 cores now, you can actually get, if you don't use it, you will actually lose 10 to 100-fold speed that you could get. So if you're looking for scalability, so typically, in fact, you see there are various things that you get out of performances, but there are limitations in terms of when you try to scale. That scalability actually is going to be limited by multiple fold, multiple orders if you don't use this expertly. Okay? And of course, it's not easy. That's why I said this actually opens up a lot of research as well, especially if you're trying to do GPU computing. So what I will try to do is to kind of categorize the problems into 3 broad categories. What is so easy and what is not so easy, and then also tell you what we have been doing. So there is so-called embarrassingly parallel problems, those which are easily divided, those which don't have any interaction between different components, and so you can solve them easily, right? And then so some of the raster data computation can be easily divided, let's say in pixels. Textual data, throughput computing, multiple instances of simulation, even though they're very heavy duty, but there are lots of instances that are easily done, right? And then so if you can use this, we should. Okay? And this is actually one of the main area where lots of computation that we typically do will fall into. Then there are those which are regularly structured computation. And the example that we saw in terms of the water flow, that falls into this category. And so I'll take one example that we have been working on. This actually is the NDVI data, vegetation data from Africa. And the idea is to find interesting regions where there's a sharp increase or sharp decrease in terms of vegetation over time. And one result is that using a single GPU with about 500 cores, we are able to process the entire image. It's actually order n square computation as opposed to linear computation. It's a quadratic computation in about 37 milliseconds. So the idea is that with this kind of speed, it's about 10-fold speed, but that actually allows you to visualize change over time, almost in real time. Right? So about 20 years of data in about 20 seconds can be done. And of course, there are other problems which also fall into this category: shortest path computation, numerical algebra problems. All interesting things. There's a lot of development in the other areas which can be harnessed here. Right? So about this Sahel data. The idea is to take this image and then see exactly where there is sharp increase or decrease. And I have a very crude demo. I may not get time to do this, but this was very interesting. And now we are actually looking at not just the longitudinal changes, the column-wise change, but also the rectangular changes over a region or over time as well. So either the rectangle or the cube, temporal and spatial both. So the embarrassingly parallel, then the regular communication pattern. And then, of course, then you have these harder problems, which are of special interest to computer scientists because they're harder. And then they're actually useful as well, is the so-called irregular, ill-structured computations. And I'll give 2 examples of that. So one is the polygonal overlay computation that this community is very familiar with. So you have not the vector, the raster data, but you have the vector data that you want to overlay across multiple layers. And then, of course, simulation, especially the discrete event simulation as opposed to time-driven simulation, where the events actually are scattered over space and time, and they're not structured. So the special overlay computation, we are very familiar with this, so I'll skip this. Here are some results on the overlay polygonal computation. So we actually had 2 years ago, had a NSF funding, a small funding from NSF and Microsoft. And the idea was to use Azure Cloud to do some interesting scientific computation. And then, of course, we happened to pick this problem through a good collaboration. That's how we got into this area, especially I got into this area. And we built a system called Crayon system that actually had 90-fold speed up for the computational part. And that was great. So idea is to actually identify the polygons in different layers, which are potentially intersecting. These are the tasks. And then you carry out the intersections. And of course, there's the input part and the output part. And that actually, the file I/O is one thing that came out to be a bottleneck, especially if you're trying to scale it. So scalability actually is the key part here, because it's easy to do things on a small number of processors, and you get good speed up. But when you try to scale to hundreds or thousands, that's when these things really constrain you, right? And so the file I/O, if inefficient task identification, load imbalance, all of those issues actually crop up. Okay. So then we also tried the various things that typically computer scientists do. That we tried Hadoop, we got some little bit more speed up, 5 to 10-fold. We try MPI, and about 10-fold speed up. But then again, these are all limited speed ups. So 10-fold is not bad, but of course you want more, right? So when we looked at what are the key problems, and task identification, of course, could be done better. So we actually parallelized R trees that this community, of course, has used very heavily. And so this is on GPU. About 200-fold speed up in constructing R tree. And then we used R tree. So the idea was to then do the distributed computing using MPI, and then within each node, do shared memory computing using multi-cores, and then also harness the GPU. So you have these three things together. And so at this stage, we have about 40 to 70-fold speed up, depending on the kind of data that we are dealing with on a Linux cluster, right? Which actually is quite decent. So something that takes you about an hour, could be within a minute. And we're, of course, going to be working on this more. So here is the system view of this, what we call MPI GIS system. So you have the MPI part on the left side. The middle one actually is the pthread part. That is for multi-core. And then you have the pink one, which is the GPU side, right? And you have to harness all of that to effectively get this kind of speed up. Some roadmap we are. So the graph actually shows the speed up, and of course, as the time comes down, so you have both depicted there. Roadmap, we are continuing to use more of GPU, and I'll tell you where. And we also would go into FPGA. There's another accelerator that is there to be used, right? And all these accelerators are typically within the node, and so you really have to harness all these things very, very effectively. Okay? And of course, the parallel I/O part, and then other things. Okay? One more example of the irregular problems, ill-structured problems, and which is actually the simulation, especially the discrete event simulation. So agent-based simulation, for example, is being done. There's a collaboration with Kent State, Eric Schuck, and Xiaowen Wang's group, and we are interested in trying to do this. This is actually right now time-driven, but could also be done in an event fashion. VLSI logic simulation, traffic simulation, these are actually all different kinds of simulations which are driven by events which are across the simulation space, scattered not very regularly, and then they actually have different pattern of computation. So it's actually one of the hardest problems in terms of trying to parallelize. Okay? So we have algorithms which are optimistic, so you simulate different components without really synchronizing much, and of course it will catch up with you, and then you have to roll back. And the idea is to reduce the rollback frequency, manage the space, all of that very well, and we have algorithms which provide almost no rollbacks and then just one backup state. And then the key to that, of course, is event queue management in parallel in a shared environment. And that's the key to synchronize the entire simulation space by trying to pull the topmost, earliest events collectively. And so this actually is I do a lot of theoretical work and then implementation of that. So it really has to be grounded in theory. So PRAM model actually is a shared memory model used by computer scientists, and we have log-n time processing over lots and lots of events which can be extracted to be simulated. And this actually has a linear speed up, order p speed up, which has been implemented now using pthread, and now in fact most recently on GPU, and we have about 40-fold speed up using that, and we are actually using that for a variety of things. And there's a little picture on the right shows kind of the heap structure, which is a wide node structure, and how it can be managed in a pipeline fashion. They actually have papers behind it. There's interest. I'll also relate a few things which is being done recently. So for example, algorithms for clipping, polygon overlay. There are lots of sequential algorithms, but there is no effective parallel algorithm. So we actually just designed one algorithm. The idea is to clip 2 polygons fast, and that might make sense if there's a very huge polygon, right? Or a bunch of polygons. And so you can do operations like union, intersection, and so on. And of course, the algorithm runs proportional to how large the input is. That's expected. But you don't want that to be, you do want that to be impacted sometimes by how large the output is. So if the output actually is small, you want that to be faster. If the output is large, then of course you want that to be slower. So you want something to be output sensitive. And that's the key aspect of what we have developed, which especially in this case, if there are not too many intersections, you have fewer things to output. And the algorithm should not be quadratic. That's the state of art right now. And so we actually have output sensitive algorithms on a theoretical model, and just coming out next month. Using plane sweep parallelization, we have order log n. This is again a very highly exponential speed up with using linear number processors in the output size. Two methods, either you use the plane sweep or use traversal method. And the state of art, I just said, actually has order n square processors, no matter what the output size is. So that's the improvement here. And that's the theoretical algorithm right now, and we have to, of course, take it to implementation, right? And so we are looking at multi-core, we are looking at GPUs. There are some preliminary implementations. Also, apart from those classifications that I showed you, embarrassing, parallel, regular, and the irregular, it's also important to look at what the state is right now, how much code is there, and where the community is going. And community, of course, is also looking at cloud. And there's a lot of code already there, especially there's a lot of MPI code. MPI actually is the de facto standard for distributed computing, right? And it makes sense to try to make this easier for community to port onto cloud, especially the Azure cloud that we have been working on. So we have a platform which actually what we're calling Cloud MPI, that essentially idea is to enable the messaging that you do and the communication among the processes, all of that. So we are at a point that we can actually get, with some more research, a compiler that could compile an MPI code to the Azure, right? And the left curve actually shows, if you're going to the cloud, I think one of the key things that happens as opposed to the high performance computing clusters and such, is you lose efficiency of communication. That is not deterministic, right? But as you go to larger and larger messages, as opposed to very short message, things become reasonably fine, right? And so that's what this shows. The green actually is the message size. And these two kind of approach, cloud MPI versus MPI, pure MPI. So larger messages actually are better, and that's the whole idea of distributed computing, that you want to coalesce a lot of things that you want to send, that you want to communicate across. And on the right, there is a crayon system that I talked about earlier for polygon overlay, which has also been ported to Cloud MPI, and it's performing reasonably well. What you see in the red, by the way, is the bottleneck. Red is the task creation, also some input file that processing. Those are actually things that we need to work on. Okay, but the computation itself actually is sharply reduced, which is, I believe, in the purple. Okay, it may not be easy to see, and again, there are papers behind it. So time to actually kind of wrap up and also tell you about the roadmap. So this, this system that I talked about, MPI GIS, of course, we are trying to leverage that with community research. So here is our vision to do both computation and data analytics. And in the PyCell system from Arizona State, Sarjakoski, and Special Hadoop from University of Minnesota, that's Mokbel. We want actually these to kind of get integrated to do various kinds of computation with usability aspect addressed by CyberGIS portals. So collaboration with Xiaoweng's. And of course, there are other things which actually we have to be looking from the computer science point of view, which is the partitioning, load balancing, the data structures within, so R trees, TPR trees, and then others. Parallel I/O, so NetCDF. This is a collaboration with the Northwestern. So this, in fact, is something that we are planning out, and then we will start implementing with the MPI kind of, Hadoop kind of distributed computation combined with CUDA as well as multicore, right? And with parallel file system. So there actually is a demo here. This is actually a very crude demo for this interest interval computation, and I don't know if this actually will work here. This is being computed on a single GPU, and this is the file I/O. This is about 20 years of data for the African Sahel region. And these are interest intervals being depicted. And what actually is useful, I don't know if you can see this, is this is being computed in about 34, 35 microseconds. So point is that this potentially, ignore the bad demo here, is a real-time system which can be used for supporting maybe decisions. Maybe this is insightful to those who actually know about this area. And so this is on a single GPU, could be done on a laptop. So the point is that this actually is very powerful for things that we want to do. Okay? And then, of course, we are going to 2D. This is a single dimension. We are looking at temporal aspects, so maybe 3D. And as you go to many dimensions, of course, the quadratic order becomes cubic and so on. Right? And so then you have to harness multiple GPUs. You have to harness a cluster. Right? And so we are doing all of that, and maybe potentially a FPGA. So we are looking at all of that. Okay. All right. So let me stop here.
Thank you. Questions for Sushil? Mike?
You mentioned parallel net CDF, and you said Northwestern. Is that something that's already developed or in development?
So the PNet CDF is already developed, and the idea is to harness that within our system. Yeah, this actually is a good community of support, and there's a lot of activities going on there. This is also with the Argonne National Lab. Yeah.
Mike?
One of the problems with GPUs is the small amount of cache that they have actually on board, and the problem of moving data to and from disk or from some other host processor. How have you dealt with that?
So there are lots of problems, I think. So that's what makes it interesting, of course, right? So of course, the file data itself, you bring it to the GPU, bring it to the CPU first, then of course the CPU, GPU data transfer, that's actually a major problem. Also the coordination, the kernel calls. Then even within the GPU, if you have the data there, between the GPU global memory to the shared memory to the cache. I mean, so there's a lot of memory hierarchy to deal with. And that is one of the key constraints that one has to play with, right? And so the results that we have shown, of course, is addressing those issues. And then, so that's a major issue. Other issues are, of course, that within GPU we have lots and lots of threads, thousands of threads, and they have to be managed well, especially in terms of, again, memory coordination. So you have to have, for each war, which is about 30, which is 32 threads, you have to make sure that they actually access the memory in a coalesced fashion. If you're accessing all over, then of course you are paying for it, right? It is difficult, and that's why it's a research area, right? So that's why my students are very interested, because they actually see potential for doing good work from computer science point of view also, right?
If there are no other burning questions, let's thank all the speakers for their excellent presentations.
Thank you.
And